Welcome to the Ad.podcast again, and we have Pierre Pureur with us today, and I've tried hard to say his name properly, and with the French accent, I guess the R's are the most problematic, but I will allow Pierre to say his name himself.
Hi, Vaughan, and thank you for having me. My name is Pierre Pureur. That's the correct pronunciation, but don't worry, nobody, not even my wife, can pronounce it correctly, so you're in good company.
Oh, good. So look forward to interviewing you today. Actually, this is our second interview. The first interview had some technology problems with it, so we're re-recording, and I think this is probably a bit better episode, less questions. So in inviting Pierre to join us, he is now an independent consultant and kind of retired from Travelers Insurance as a chief architect in Connecticut area. What are you doing these days, Pierre?
What am I doing these days? Basically writing. I'm writing quite a few articles, which are published on LinkedIn. I'm also working on an article that's going to come out hopefully on Stack Overflow. So we'll see. And giving some podcast.
So explain to it, you're a co-author of the book Continuous Architecture, and this is in the setting of the cloud and Agile and DevOps these days, which is very popular. So can you explain to us what is continuous architecture and how would you define it?
Absolutely. So we actually... Margaret Herder and I introduced the concept of continuous architecture back in 2016. That was the first continuous architecture book. And at the time, we organized a continuous architecture around 6 principles. Simple principles. They're really how we think, they describe how we think about architecture. So in no particular order, the idea was, the first one, think products rather than projects. Nothing really revolutionary, but it's important. Focus on quality attributes. Don't try to architect according to functional requirements, but quality attributes are what's driving the architecture. The third one, delay design decisions until they are absolutely necessary. Don't really rush. Don't rush to design. Try to design based on facts, not on basically on what you think could it be. Fourth one, architect for change. Try to, as much as possible, think small, but not too small. There is a balance on the small there. The fifth one was really about architect for build, test, and deploy, as well as operate. That's important because most of our architects think, okay, so we're going to build a system, we're going to architect around that, and we're going to throw the code above the wall, and somehow it will run. Well, we think that it's important to think also how is it going to be tested, how is it going to be deployed, how is it going to be operated. And that has big implications on things like resilience and scalability. And the last one was really, the first 5 were really technical. The last one was more about your organization, the way you model your organization really drives basically the design of a system. That's what is known as Conway's principle. And try to think in terms of how do you want to organize your teams to basically deliver a system which works well. So those were the 6 basic principles. And we thought about those principles, say, oh, that's great, okay? But they really describe how we think about architecture. They're not really very prescriptive. So the idea of a new book was we complemented the principles with some essential activities, which really drive you to producing an architecture design. And the activities are focused on quality attributes, because quality attributes are very important for the architecture. They actually drive the architecture. Drive architectural decisions. Decisions are the most important unit of work for an architect. Know your technical debt. No matter what you do, you're going to create technical debt. So you're going to have to deal with that. And it's kind of pay me now, pay me later. And then, most importantly, implement some feedback loops. So, because nobody is right the first time, the second time, the third time. You put something out there. and you look at the feedback, and you basically adjust your architecture, your design. So those are the activities. And then on top of that, we have a toolbox that really things are well-known tools like tactics, logs, decision logs, utility trees, and so on and so forth. So that's in a nutshell what continuous architecture is about.
Thank you for describing that and the 6 kind of principles behind it. So I think a lot of listeners would say about themselves that they are following a sort of shift left approach. And as I understand, maybe there are different nuances on shift left, but if we think of a timeline as reading or following a time increase from left to right, where left is earliest and right is farther away, that means that we are starting to do certain things earlier in the development process. How would you describe shift left and maybe a bit more in detail? And also, so if we are using shift left approach, do we still even need architecture now?
Yeah, that is a great question. I think what's happening is things like DevOps, now DevSecOps. I'm not sure what comes next. I mean, we move the DevOps to the left, the Ops to the left, and when we move security to the left, and so we're shifting everything left. So I'm not sure what's going to be left on the right. But all these things have really blurred a lot of roles, okay? And including architecture. Architecture is being blurred like many roles. And the interesting thing is that responsibilities still remain. We may get rid of a role, but the work still needs to be done. Things like performance engineering, security engineering, and usability engineering still need to be done. So the bottom line, if the architecture is not suitable, then specialized tooling, specialized processes are not going to rescue the system. So you need somehow to have a solid foundation of architecture. I mean, that doesn't mean, by the way, that you need architects. It just means that you need somebody, or actually a group of people with skills that can actually provide that function. So what happens actually is kind of interesting, because a lot of people think they shifted left. So they brought basically the ops to the left into the dev thing. They brought security in dev as well. And now they're feeling good. And they say, oh, we shifted left, we're done. Well, not so fast, because what's happening is there's still a need for what I call continuous architecture. Architecture is really turning more and more into a continuous flow of decisions. And as a result, you need to actually take care of a number of things, even if you shifted left. So the project continues, you still have to deliver the product at some point. And you need to do things like basically architecture decision review or design decision review. You need to review risk continuously. Okay. You need to update your fitness functions, for example. You need, if you're interested in security, you need to continuously do reviews of your threat modeling and monitor your metrics. And all these activities continuously go on even long after you actually put a system in production. So shift left is kind of illusion, a bit of an illusion, so to speak. It's really, you need to think continuously about what you need to do throughout the life cycle of the system.
Very good. So, well, we need architecture. And I think this leads to my next questions. And I have 2 questions about what used to be known more formally as non-functional requirements, but it's taken on not only a new name, but a bit of a new meaning, and that is quality attributes. So I have a couple of different questions about quality attributes. Why do quality attribute requirements drive software architectures?
Okay. So I'm glad you actually went back to quality attributes, because I know it's a small thing, but I do object a little bit to people using non-functional requirements. I mean, it sounds like requirements for a system to be non-functional. It doesn't seem right to me. Anyway, so any blob of software can satisfy functional requirements. You don't need to architect the blob, right? You just can throw some code out, run it on a very large server, create a very large monolith, and voila, you're done. Okay. Problem is, if you do that, you're going to find out very quickly your system is not going to last very long. In order for a system, for the architecture to be, or for a system actually, software system to be resilient and to last a long time at a reasonable cost, you need to think about what are your quality attribute requirements. And that's why we think that QARs shape a system. And they are really, really important. Here's the catch. Usually, they are badly defined or they are poorly defined. It's not unusual to look at things like, oh, the system must be fast, or the system must be resilient, or the system must be scalable. I don't know about you, Vaughn, but I don't know how to design a system based on that. And unfortunately, a lot of us get that from our customers. And when we push them, they usually come up with estimates that don't really make a lot of sense, which drive to either under-designing or which even worse, over-designing. So we really believe that, quality attribute requirements, if you're going to drive the architecture, must be well-defined. And the way we think, nothing is really best. I mean, I hate to say the best way because that's right. But an efficient way based on my experience, an efficient way of doing that is to use a technique which was really made popular by the SEI CMU, Carnegie Mellon SEI, which is really as part of their ATAM architecture trade-off methodology. They came up with a concept of scenarios. And the idea really was really about you create some scenarios that you define very carefully about, for example, scalability. And you define those scenarios they actually had more dimensions, but I usually use 3 dimensions for my scenarios. One is stimulus. So, for example, if we think about, basically, if we are looking about performance, okay, stimulus is going to be someone is using a system. Could be an external user or could be an outside force, but something is using a system. Response means what does the system do in response to the system? So, for example, if a user decides to use transaction XYZ, what does the system do? And then measurement, remember we're talking about performance here, is how quickly or how slowly does the system respond. And what we're finding out about this way of dealing with QARs is that it forces you to be very precise and define exactly how you want to measure your quality attribute requirements. And this also forces your stakeholders to actually tell you in more precise terms what do you actually need, as opposed to a system that is fast, a system that is scalable. So in terms of QARs, QARs have changed through my career, okay? And I won't even bore you when I started, but from my career, what I've seen is QARs have evolved in terms of what are the most important ones. In this age of digital, we really think that there are 4 of them that are really important: scalability, performance, resilience, and security. I don't have to convince you on security. I'm sure that everybody understands the value of security. Okay, performance, well, obvious, right? I mean, if the system doesn't perform well, then nobody's going to want to use it, so the system will die very quickly. Scalability is one which was not very popular 10 years ago, but has become almost overpopular, extremely popular because of the large e-commerce companies, Google, Amazon, Facebook, that really have made scalability kind of number one. And then scalability, when it's interesting with scalability can go up or down. We'll talk more about scalability in a minute. But if you look at what those companies have done, it's quite admirable. They have done a lot of good work based on scalability. But that work is not for everyone. You are not Google. You are not Amazon. Unless, of course, you work for Google, you work for Amazon. But most of us are not. And the tactics that those companies use are usually not very applicable to most of us. And the last one is resilience. So resilience, I mean, I keep on talking about a small story, part of COVID. I mean, that's the whole pandemic going on. And part of COVID, what happened is there was a lot of people who had more time to work from home and had a lot of time on their hands. And they started basically trading securities, which is something we all do now. So trading securities became, instead of going through an advisor, you actually were able to trade, and you're still able to trade directly. And that put a lot of onus on the trading systems. If you think Robinhood, not to mention them, but if you think Robinhood, for example, look at the number of outages they had basically over the last 2 years. It's kind of interesting. And we could argue that, their goal was to get out of the gate they were a startup initially, and to get a system out there, an MVP, basically a minimum viable product, and get people to use it, which they did very well. Unfortunately, they were the victims of their own success. And I don't think that, and again, I don't have any special insight on how they architect their systems, but I don't think that anybody, or I don't think a lot of people at Robinhood thought about how quickly they needed to basically scale up and how they had to be resilient. The problem is there were days, of course, there were huge swings in the market and still going on. And those are the days where people really are trying to trade. That's normal. You see your portfolio going down or up, and you try to take advantage of that. And people are trying to trade, and suddenly those systems are not available anymore. And that's not only the case with Robinhood. It also happened to large, I won't mention any names, but it happened to very large, well-established traders. So there's a lot of, resilience is hard. It's a difficult quality attribute to satisfy, but it's definitely, if your system is not resilient, you're going to find out the hard way.
Yeah, for sure. There's a lot of wisdom in your statements there. Thank you for commenting on that. Now, I want to just preface my next question about, the quality attributes around, let me just say that to people who are listening to this, who are into domain-driven design, this may sound kind of foreign to them because functional requirements are, in essence, what domain-driven designers are really interested in. But if we take from a pure architectural standpoint, why are quality attributes more important than functional requirements from a pure architectural context?
Okay, so it's actually quite simple. Basically, we are back to my statement of quality attributes shape the system. And if you ignore your quality attributes, you're going to basically design a system that basically will run for a little while. But, will it perform? I don't know. Will it scale? Probably not. Will it be secure? Probably not. Will it be resilient? Not really. So, especially if you talk about a system that's exposed to external users, it may well be that your system is not going to last very long. So, honestly, I think that without quality attributes, there is no architecture. You can't really design your architecture.
Okay, so it kind of sounds to me like the quality attributes are something that, I don't know, maybe we can get a sort of some of those things for free in the cloud. I mean, do you think that I'm not saying that you don't have to think about this because, our vLingo Zoom platform has resilience tooling in it. So yes, you have to think about resilience and design in resilience. But in using Kubernetes and in using Amazon or Google Cloud or Azure, do any of those things become easier, or do you think it's just as challenging as it would be in a data center?
So I believe that a badly designed system, if you port it to the cloud, will still be a badly designed system running in the cloud. There is no escaping that. So if we take scalability is a little bit easier to discuss. Now, resilience gets a little bit involved, and we don't have the whole day, unfortunately. But if you take scalability, for example, so there are a couple of misconceptions out there about scalability. One of them is that, my system runs in the cloud. So scalability is the problem of a cloud provider. And sometimes, and you're absolutely right, Vaughan, I mean, the same goes for resilience, same goes for security, and not quite. It doesn't go that way. Okay. If you really take a badly designed system, something that really runs badly, doesn't really scale on your own computers, and you want to say, oh, you know what? I'm just going to take the whole thing. And usually those things come under are designed as a large, one big code base, and nobody really knows too much what's going on there. And probably, kind of system that started their life on a mainframe, probably, half a century ago. And you kind of run that through some kind of code transformation, because clouds usually don't run COBOL. I mean, I don't know, I could be wrong on that, but I don't know too many clouds that run COBOL. So just take your old kind of vintage, kind of 2000 or maybe 1996 kind of COBOL, CICS kind of system, and you transform it like some black box, and you turn that into something that looks more modern, and you kind of port that to the cloud. What you're going to find out very quickly is, number one, it's expensive, not only to port, but also to run that on the cloud. And number two, your system is not going to be scaling any more than it was scaling on your own infrastructure. The problem with cloud is that the cloud runs well. Systems are designed for the cloud. Okay, so unless this goes back, remember my principle about basically architect for not only for build, also for test, deploy, and operate. If you know you're going to operate on the cloud, you have to architect for the cloud, unfortunately. There's no such thing as saying, oh, I don't really care. I'm going to create a system that runs on this amazing, virtual computer that doesn't exist yet. And I'm going to put that on a real computer and magic happens. Doesn't. There's no magic there. So, that's one misunderstanding. The other misunderstanding is really calling a system scalable. Okay. So people say, oh, my system is scalable. And my answer is, what do you mean? Do you mean your database is scalable? Do you mean your code is scalable? What exactly do you mean by that? In reality, we found out that most of the time, the first thing which causes scalability issues is the database. Okay, the code usually will last a little bit longer in terms of scalability than the database. So when people tell me my system is scalable, my first question is, okay, show me the scalability test you have run against your database and prove to me your database is scalable.
Yeah, interesting. So I haven't wasted my breath then in saying, don't count on Kubernetes or Kafka or the cloud to solve all your problems.
No.
Yeah. And very, very good explanation of that. Okay, let's kind of shift here a little bit and get into another aspect of architecture. Why do you think that architecture decisions are so important, and how do you personally or the teams you've worked with go about tracking architecture decisions?
So it's actually, I'm glad you're asking this, because one thing that this is a big difference between the first book and the second book. The first continuous architecture book, we mentioned decisions. But at the time, for us, decisions were important, but other things were important as well. The second book, which is basically 5 years later, based on the work, and also Owen Woods joined us as the third author as well, and based on a common experience, we started saying, you know what? This continuous thing really applies to decisions. Architecture decisions is what remains when everything else has faded away. If people think of architecture as, and we all do, right, very nice little diagrams, or not so little, because usually architects love to create diagrams. And architecture diagrams, the more complicated, the better, because nobody can really read them except the person who actually created the diagram. And that makes that person look very smart. And who doesn't like to be looked as smart, right? So the whole concept of diagrams, and diagrams is important, but diagrams are just a way to communicate something to someone else. And if someone else cannot read your diagrams, you're not communicating. So you basically waste your time. And diagrams, honestly, I mean, from time to time, Vaughn, I don't know if you've played that game, but I like to do that from time to time. I go back to my archives and I look at some architecture diagrams I created 10 or 20 years ago and I have a big laugh, because usually, number one, I can't even read them anymore. And number two, I say, what the hell was I trying to do? Okay, diagrams are very temporary. They don't do well with time. They just decay very quickly. What is important are decisions. Now, the trick of the decisions is how do you make sure that people remember them? Because if you make a lot of decisions, you need somehow to document them. Now, I know most people don't like to document, but certain things need to be documented. And suddenly, when someone makes a decision, that needs to be basically documented somewhere. Now, the best way to keep decision in sync with the ultimate artifact, which is the code, because the code is really what we produce at the end of the day, is really to keep your decisions very close to your code. I mean, if you keep your code in GitHub, then by all means, keep your decision in GitHub. Okay? There's no magic bullet there. This doesn't really matter where you keep your decisions, but so long as you keep them somewhere and you know where they are. Okay? And also, so when you make decisions, it's important to actually think in terms of, okay, so what was the context of that decision? Because if you look back at 10 years later, you probably forget what the context was. So document the context, document who made the decision, when the decision was made. And one thing I really like to do with my decisions is let's document the alternatives. What else did I think of? What else did I reject? And then why did I decide to go that way? And then I would just for one more kind of at you at this point. What is the cost of undoing the decision? What if I was wrong? Okay, no matter how smart I am, I'm going to make wrong decisions. So at some point, I'm going to basically unwind the decision. What's the cost of doing that? And I think that most people don't like to think about that because number one, they like to think that they make the right decisions, whatever right means. Okay, and number two, they don't like to think that, oh my God, at some point, maybe I was totally wrong, and the system that I thought needed to be scalable for a gazillion transaction only needs to be scalable for 10 transactions a minute. That happens.
Yeah, for sure. So there are a number of architecture decision record templates out there, and I think most of them are meant to be put into a code repository of some kind. Michael Nygaard's is the one that I've used, and maybe you have, and others. Well, he has a recognizable name.
Oh, yeah.
He's smart, so why not? So, okay, good. And it is important to keep those and look at them from time to time, as you said, review them. Okay, now we already sort of talked about the quality attributes, the ilities, and does the cloud take care of scalability? Well, as you said, there are some aspects of the cloud that make scalability more realistic, but of course our actual application design and our architectural decisions and designs are quite important. So why do you think that scalability is particularly an architecture concern, and how would you define it?
Okay.
Start out with those.
Yes. So let's define scalability first, because that's an important thing. So the way I think of scalability, and everyone may have a different definition, but the way I think of scalability is really the property of a system to handle an increase or decrease amount of workload by increasing or decreasing the cost of a system. And I think that it's important to think in terms of decrease as well as increase. Everybody thinks, okay, so my system must be scalable, meaning that, okay, right now I will be able to process 100 transactions a minute. So 6 months from now, I should be able to process 200 transactions a minute, and then 1,000 transactions a minute, and so on and so forth. Okay, but what if suddenly my volume goes down and I need to process 10 transactions a minute, or maybe 1 a minute? If you think about a company like Amazon, okay, Amazon goes for peaks and valleys. Right now, it's probably the most busy part of the year for them. You know, we're going into Black Friday, we're going into Cyber Monday, and so on and so forth. And basically, volumes increase a lot. But you also need to be able to shrink down and operate your system at a reduced cost when volumes are no longer what they used to be. I used to work for an insurance company in Hartford, Connecticut. And it was actually interesting because we actually had managed to recognize the patterns, the volume patterns of basically and this is retail insurance. So volume patterns during the week. Monday was a fairly quiet day. Tuesday, and don't even ask me to explain why, because Tuesdays used to be very busy. Then volumes will go down Wednesday, Thursday, and Friday. Okay, and again up Monday, peak on Tuesday, and so on and so forth. And if you talk about Thanksgiving, basically, and some insurance we used to sell was car insurance. So do people buy more cars on the Thanksgiving weekend? I don't know. But certainly we had a peak of volume the Monday and the Tuesday after Thanksgiving. For a company like the one I used to work for, it was very important. Those were the pre-cloud days. So it was very important for us to actually be able not to over-dimension our infrastructure, and therefore have systems that could gracefully scale up or scale down. And I think that's one aspect of scalability that people forget. Scalability needs to be thought in terms of, can I scale up? Yes, we want to fix of that. Can I also scale down? Also, did I over-provision my infrastructure based on what my business users told me, which is, our forecast, our business expectation tell us that we're going to be able to sell, again, a gazillion policies a year. So why not dimension the system for that? Well, why not? Because that costs money. And another oversized architecture running on an oversized infrastructure is an expensive thing.
Yeah, for sure. And unnecessarily absorbing those kinds of costs, it's just something you can avoid. In reactive architecture and programming, we call that elasticity, right? So it gives a good idea of being elastic. A system can scale out dynamically as load increases, as load decreases. We scale back in, and we're basically using exactly what we need at any given time. So that's the optimal.
Yeah. Always keep in mind, basically, the cloud provider needs to make a living. And Amazon are very good at making a living, as we both know, not to mention them. But basically, they're, part of what they love is people who run basically over-dimension systems on the infrastructure, because that way they can actually sell you more cycles than you really need. And it's kind of important to always think of the economic aspect of the software system.
Something I more recently learned is that Amazon has about an 8,000% markup on bandwidth.
Wow.
8,000%. So if in your home you pay something for gigabit throughput, what would that be like if you multiplied by 8,000, right, or something? So
to that point, I mean, I think that one thing that architects and software engineers forget often is that cost is a quality attribute. No, you don't see that too often. People basically say, oh yeah, sure, performance, scalability and so on and so forth, but cost matters a lot. I mean, in a real world, in a non-software or hardware world, but if you hire an architect to design a house or a boat, one of the first questions that architect is going to ask you is, how much money do you want to spend, Mr. Vernon? Always, okay? I mean, basically, there's no such thing as an unlimited budget when you create a house or a boat. You really have to limit yourself. And architects usually offer different options based on cost. I can build you the house, because it costs so much, but your budget is that much, then I can build you that house, and so on and so forth. We don't think like that. We don't really think too much about cost. And I think that's a shame, because really being able to really offer to our stakeholders, say, okay, so if you spend that much money, okay, this is the kind of system we can build for you, and this is how much it's going to cost to run it. But if you spend that amount of money, then you get a different system. I think basically our stakeholders don't realize that, and it's a shame, because we should really make that more apparent.
Exactly. Yeah, and I think that by the way, on that comment on bandwidth costs on AWS, I mean, there are a lot of companies paying for that, and maybe it's a reasonable cost given their actual uses of bandwidth, how much bandwidth they need to consume. But I think companies like Cloudflare and others are kind of offering a lot better choices in that. And I found too that some companies are now deciding to leave the cloud. It has just become far too expensive. Unlike, most of the ideas behind the cloud initially, people thought, hey, I get rid of all my staff or a lot of my infrastructure staff and admins and so forth, and we get rid of all this machinery. Look at how much money we're going to save, and then actually now they're finding out that wasn't so true after all. So then, a company like Cloudflare will step in and kind of give you way better numbers in terms of the kind of bandwidth costs. So maybe that's a specialization for some companies to consider in that way. Okay, let's kind of completely shift gears now and talk about the book. Of course, we've been dancing around the book, so to speak, by the topics that we're discussing, but let's talk about the use cases that the book was designed around. Could you describe these? Tell us why the actual examples that you used are important for a book about continuous architecture.
Well, so I think that, again, based on all of us, when we decided to tackle that project, all of us were already published authors, so we had previous experience on publishing books. And the one thing we thought about was, writing a book is great, but somehow the book needs to come alive. And what we thought about is, instead of taking a few examples to illustrate the points we're making, why not create a real case study? And as close as possible to reality, but not a full system, because that will take a lot of books. But why not create a case study that will basically be the skeleton of the book, that will basically kind of get all the parts of the book to hang together? And we decided to take a case study on trade finance, which is basically what a term that describes what companies do, the products, the financial instruments that they do to basically facilitate global trade and global commerce. And I do have a previous experience on trade finance, but that dates back from a long, long time ago, actually half a century ago. So it was actually interesting for me, and my two co-authors didn't have any experience. So it was interesting for the three of us for me to rediscover and for them to discover trade finance. And we took as an example letter of credit, because letter of credit is a fairly simple, they get complicated, but on purpose, we kept things as simple as we could. And we spent quite a lot of time defining basically what a case study would be. And what we said is, why don't we pretend we work for a software company? And that software company basically found that there are a lot of inefficiencies in trade finance, especially letter of credit. So could we really make things more efficient? Could we automate? And we actually pushed the concept all the way to blockchain. And we said, okay, could we actually, at the end of the book, you see in chapter 9, could we actually use blockchain to actually make trade finance even more efficient? So, definitely write the ultimate trade finance system. It's not meant to be. But the system is well defined in appendix. And it has, we didn't write any code, so we didn't go to that point. But we took the design fairly far. And what's nice with that is really allows us to, each chapter basically says, okay, so now we spend some time explaining to you what scalability is about and so on and so forth, and different tactics. So let's show you basically what it means for the system. And I think that made the whole book much more coming alive than it would have been otherwise.
Absolutely. And that is how I wrote the Red Book, Implementing Domain-Driven Design. Mm-hmm. And it's how Tomasz and I have written our latest book, Strategic Monoliths and Microservices. Having realistic, concrete examples of scenarios are very important. And people are going to just be able to, latch on to the idea of the architecture quality attributes that you're talking about, or whatever aspect of architecture or of domain-driven design or of any topic, if you just have a realistic example that they can relate to. So I guess maybe you could comment now, maybe recapping the discussion in this age of Agile, Cloud, and DevOps. Can you kind of pinpoint why architecture, that is software architecture, is still relevant today?
Yeah. So, I'm kind of going to repeat myself a little bit, but I think it's worth repeating. The first thing we're finding is architecture is becoming a skill, not a role. Okay. So what we're seeing more and more is the days where you had the architect coming down from the ivory tower and basically kind of dispensing some pearls of wisdom, drawing some diagrams that nobody understood. Those days are gone. Okay. Right now in a team, architecture is everybody's, I would say, I was going to say problem, but problem is everybody's task. So, which the corollary to that is that most team members, actually all team members, should really have architecture skills. So the idea of conceptualizing and being able to think concept rather than basically down to the code and so on, that's important. Okay. Architecture is really also becoming a continuous flow of decisions. Okay. It's not enough to make some decisions initially up front and basically be done with that. It's actually I think back at the beginning of October, I was giving a presentation to a group of engineers in Copenhagen, virtually, of course. I didn't go to get to Copenhagen virtually, but I was in a presentation, and they wanted really their point was how much architecture should be done up front versus through the life cycle of the system. And it's a great question because, and I don't have the answer, by the way. But the way I'm thinking about it is that at the end of the day, you got to make some decisions up front. If nothing else, one of the things you're going to need is, for example, to implement scalability and resilience, you're going to need to have a monitoring framework. Well, that monitoring framework needs to be designed initially. You can't really design that and implement it as an afterthought. Okay, so certain things need to be done up front, but not too many. That's a key thing. And I think that some decisions need to be made up front, not all of them. And it doesn't matter what decision you make, somehow you're going to be wrong. Okay, there's no escaping that. Nobody is right 100% of the time. That's why it's so important for each decision you make to understand the cost of unwinding that decision. Because I don't know how many decisions you're going to have to unwind, but probably more than you think. So the whole thing, make a decision continuously and kind of correct them continuously. Okay. So if I look back at the last 20 years, okay, there has been kind of a big conflict between people which are basically the big proponents of big upfront design. So let me design everything up front, let me make all the decisions up front. And at the other end of the spectrum, you get people who basically tell you, architecture just emerges. Think of a big whale that comes out and the architecture emerges. Neither of them, I think, are right. Okay, and the reality is somewhere in between. How far to the left or how far to the right? I'm not sure, but certainly, the way to kind of compensate for all the mistakes you're going to make, because you're going to make mistakes as you architect and design, or compensate for that is continuously make decisions and course correct. Okay, that's why also the feedback loops are so important. Because you're going to put something in production, that thing is not going to be perfect. It's going to have problems. How actually do you compensate for that? Well, with feedback loop. One extreme of feedback loop is one technique that's being used more and more for resilience, which is 10 years ago, we used to think that, okay, so the way to make a system resilient is to make sure the system never crashes. Okay, but the 5 nines, the 6 nines, so on and so forth. That's not realistic. Okay, in reality, every system will crash sooner or later. So I think it's much more realistic to say, well, my system is going to crash. What do I do if my system crashes? How do I automatically recover from crash? And how do I compensate for all the things that can go wrong? And at the extreme, how can I predict what's going to go wrong? And there are techniques to do that now. You can use AI for that. It actually works. So the whole point is really to actually recognize that nobody's perfect. We all make mistakes. We continuously make decisions and going to unwind those decisions at some point. The last point you really need to think about is technical debt. we all create technical debt, and there's nothing wrong with technical debt. Because sometimes, to level system fast, you have to take a certain amount of technical debt. What's wrong is to think that you will never have to repay that debt. Because sooner or later, you're going to have to repay it. And unfortunately, the interest on that debt accrues very quickly. So when you repay it, that's when you're going to have a big ouch and say, why on earth did I do that?
Yeah, mom won't be able to put a Band-Aid on it and make it all better. That one, right?
Band-Aids can be expensive.
Yeah, yes, these Band-Aids can for sure. So really good advice, good summary of all these points. So it sounds like, I don't actually know how many years you've spent in software development, IT, and so forth, but you did reference about 50 years ago being in a certain domain. Was that in software?
Yeah. Oh, yeah.
Yeah. So now, with this at least 50 years of experience in software development, software architecture, what are 3 points of advice that you think would be useful to all the listeners who are trying to be better at this topic of software architecture?
So this is where I sound like a broken tape recorder with French accent. But the first one is, keep in mind, architecture is a skill, not a role. Architecture is not anymore the purview of the architect. And I'm not even sure there's such a thing as an architect anymore. This was one of my last talks at Travelers, which I gave and to an audience of architects. And of course, that was kind of received with some interesting faces. But it's a fact. Architects basically are, I think, on the way out. Basically, architecture is becoming a role, a skill, not a role. And that's critical. The second point is, think about this continuous flow of decisions. And some of them are going to be right. Some of them are going to be wrong. Hopefully, we're going to make more right decisions than wrong decisions, but we don't know. And the key thing is continuously making good decisions and course correcting. And that's very important based on the feedback you get from the system. The last piece of advice is basically always, yes, it's nice to architect to build a system, but think about monitoring. That system is going to have to grow in production. It's going to have to be monitored. How do you build a monitor framework around that system? If you don't think about it early in the process, it's going to be very expensive to actually do that monitoring framework. Same way with dealing with failure. Your system is going to fail sooner or later. There's no escaping that. So how do you deal with that? I wish that people who build trading systems would have thought of that back 2 years ago and say, okay, so what if our system fails? What if we have this crazy trading day? And what if we can't really run the system anymore? What happens? So I think it's much better to actually think about it a little bit before it happens than after it happens.
So it's not repetition like boring repetition. It's repetition for emphasis to make sure everybody understands. And we love your French accent. So
thank you.
Don't worry about that. So thank you so much for talking today. And, you made a comment there that I'm just going to key in on this. If architecture is a role, not a position, right? Or it's
a skill.
Maybe I didn't even say that correctly. It's just something that people, software developers do now, right? They share in the architecture. So it's not, I guess what you said is it's not a role, being that it's not a specific title. Now, if this is becoming the responsibility of even burgeoning software developers, I'm going to say that they need to pick up your book and learn how to use software architecture, decisions, to pay attention to the quality attributes, to be able to share in this with more experienced software developers and do architecture, right? Architect software, and because it's now everybody's responsibility to do that.
Yes, absolutely. I think that the role is becoming software engineering. And I like the term engineering because it's really, a software engineer, to me, covers the whole gamut, all the way from architecture down to coding and testing as well, and operation as well. So I think what we're probably witnessing is the dawn of an era where we're going to have a lot of software engineers. Now, some of them may be more specialized in some aspects because it's impossible to specialize yourself in everything. You can't be the expert on everything. But we're going to have those teams. And those teams, back to Conway's principle, right? Those teams to be needs to be organized in such a way that you don't have a lot of long communication lines. Communications are really facilitated. And some people are going to have more skills, for example, in architecture. However, everybody in a team needs to have architecture skills. Everybody in a team needs to have coding skills. Everybody in a team needs to have design skills, of course. Everybody in a team needs to have testing skills and even security skills. Security, well, we didn't talk about security today, but security, one fallacy about security is the problem of the security people. Wrong. Okay. Security is becoming everybody's problem.
Exactly. And nothing is ever completely secure. So there's a lot of work to do in that area. Okay, so I've actually already said goodbye, and then we have to say goodbye again now.
Thank you.
But it's been a very big pleasure to speak
Same
with you
here.
again, Pierre, and let's stay in touch. And
Absolutely.
maybe we can have an update to this after, the book has been out for a year or so, which is will be like June of 2022,
year, yeah.
right?
Thank you.
Yeah, good. Okay, we'll see you, Pierre.
Take care.